So imagine for just a second that you are tasked with building the world's most powerful supercomputer.
Right.
But instead of doing what, literally everyone else in the industry is doing, so instead of building this billion-dollar ultra-sterilized clean room filled with rare earth metals and toxic chemicals and massive vats of liquid helium.
Which is the standard right now.
Right, the standard. Instead of all that, you decide to build this thing using a 3D printed carbon sponge, a laser, and basically the exact same atomic material that makes up the lead inside a standard #2 pencil.
I mean, it sounds completely absurd.
It sounds nuts.
Yeah, if someone pitched that to you, it sounds like a middle school science fair project that somehow just got totally out of hand. But, in the context of the current global race for quantum supremacy, this bizarre-sounding approach might actually be the most elegant and, frankly, disruptive solution the physics community has ever seen.
I am so ready to get into this because what we are unpacking today is a technical white paper that was released in April 2026.
Yeah.
And the technology being proposed here is called quantum lattice. It's describing this monolithic, all-carbon 3D quantum computing platform. And our mission for this deep dive is to basically tear this white paper down to the studs.
Absolutely.
Because if the physics and the engineering claims in this document actually hold up to scrutiny, and it completely shatters the massive cryogenic infrastructure bottleneck that is currently suffocating quantum computing.
Yeah, it changes everything.
Think about what that actually means for you as the listener.
Yeah.
We are talking about moving from delicate machines that require room-sized, multi-million-dollar sub-zero freezers to dense, highly scalable, room-temperature quantum tapes. Like tapes that you could practically spool out like a roll of film.
Yeah, to really grasp the stakes here, I think we have to look at the physical reality of quantum computing as it exists right now today.
Set the stage for us.
Okay, so it is entirely bound by its environment. The qubits we use today are almost tragically fragile. By their very nature, they want to interact with their environment. They want to, share their quantum information with the universe.
Right.
And the moment they do that, they lose their quantum state. They collapse.
Decoherence.
Exactly, decoherence. So to prevent that, the entire industry has sort of resigned itself to isolating these chips in extreme vacuums and freezing them to temperatures that are actually colder than the ambient temperature of deep space.
Which is just wild to think about.
It is, and it's a logistical and infrastructural nightmare. So if this white paper has truly mapped a path to bypass that cryogenic requirement using nothing but highly structured carbon, I mean, it doesn't just advance the timeline of ubiquitous quantum computing, it fundamentally rewrites the rules of what a computer is physically allowed to look like.
That's the crux of it, right? It's the difference between a quantum computer being this rare, mystical mainframe that only a giant tech monopoly or a sovereign government can afford to run versus a quantum computer being something that could fit inside a backpack.
Or be deployed in a Humvee.
Yeah, or just sit on a researcher's desk. But, okay, before we can understand why an all-carbon sponge is such a revolutionary leap, we really need to ground ourselves in the frustrating physical limits of the current state-of-the-art machines.
We need to know what this carbon sponge is competing against.
Exactly. Let's set the stage of the industry right now, April 2026. What exactly are the heavyweights building?
Well, the landscape today is overwhelmingly dominated by two incumbent giants, so IBM Quantum and Google Quantum AI. And to be fair to them, the engineering leaps they've made recently are astronomical.
Oh, absolutely.
IBM is currently rolling out their Heron R3 and Nighthawk architectures. So we're looking at chips hosting roughly 120 to 156 physical qubits each. But their really big achievement is shifting to 300 millimeter semiconductor wafer fabrication.
Right, getting it into the standard factories.
Yeah, they've managed to take these incredibly delicate quantum circuits and integrate them into traditional, mature silicon manufacturing pipelines. It's a massive push for industrial standardization.
And what about Google? Because I know they've been pushing heavily on like the algorithmic and error correction side of things.
They have, yeah. Google Quantum AI recently deployed their Willow chip, which is sitting at 105 qubits. But the sheer qubit count isn't really the headline for Willow.
Right.
The big news is that they recently demonstrated below-threshold surface code error correction.
Okay, break that down for us in plain terms.
Sure. So in plain terms, that means for the first time in history, their logical error rates are dropping exponentially as they scale up their error correcting grid.
Wow.
The more qubits they add to check for errors, the better the system actually performs, which is a massive threshold to cross. Plus, just last year, they ran the quantum echoes algorithm.
Oh, I remember that.
Yeah, that was a watershed moment because it demonstrated a verifiable quantum advantage over classical supercomputers by a factor of 13,000.
13,000 times faster for a specific calculation than the biggest classical supercomputer on Earth. That is staggering.
It really is.
So on the surface, things look great. Both of these platforms are making incredible progress, but there's this massive looming wall they're about to hit, right?
Yes, there is.
Because both IBM and Google rely on an architecture called superconducting transmon qubits. And these transmons suffer from what the industry calls the dilution refrigerator problem.
That is the wall.
Yeah.
So superconducting transmons operate using microscopic loops of metal interrupted by insulating gaps, which are called Josephson junctions.
Right.
And for these circuits to exhibit quantum mechanical behavior without being completely drowned out by ambient thermal energy, they must be cooled to roughly 15 millikelvin.
I always try to pause when we throw numbers like that around because the human brain just struggles to comprehend how cold that actually is.
It's hard to visualize.
Right, because absolute zero, the theoretical temperature, where literally all atomic vibration completely stops, is 0 Kelvin. 15 millikelvin is 0.015 degrees above absolute zero.
Yeah.
Outer space, like the actual void between stars, is naturally warmed by the cosmic microwave background radiation to about 2.7 Kelvin. So we are talking about engineering a localized environment that is roughly 200 times colder than the vacuum of deep space, right here in a laboratory on Earth.
And doing that requires an astonishing piece of machinery called a dilution refrigerator. If you've ever seen pictures of a quantum computer in the news, you are usually just looking at the fridge.
That beautiful tiered golden chandelier thing.
Exactly, that chandelier of wires and plates. These machines use a really complex thermodynamic cycle, mixing helium-3 and helium-4 isotopes to constantly siphon heat out of the system.
Yeah, they're huge.
They take up enormous amounts of space and consume megawatts of power. But here's the critical bottleneck, and it's important to understand this. It's not just generating the cold that limits us, it is the wiring.
Because you can't just put the chip in the freezer and close the door. You have to actually talk to it.
Exactly. Every single one of those 150 qubits needs to be independently controlled with microwave pulses, and the results need to be read out. That means you have thousands of microscopic coaxial cables running from room temperature classical computers sitting completely outside the fridge, routing all the way down through the temperature stages, right down into that 15 millikelvin abyss.
And thermodynamics dictates that heat is just naturally going to travel down those wires.
Right.
Every single one of those thousands of cables is basically a microscopic thermal highway trying to let the heat back in.
You've nailed the mechanics of the problem right there. Every wire is a thermal leak, and this imposes a hard, unforgiving physical limit on your physical qubit density.
Because if you add too many wires,
The heat load from the wires would instantly boil off your cooling capacity. You simply cannot cram millions of superconducting qubits onto a chip if you are required to physically route millions of cryogenic cables down to them.
the fridge would just fail.
The fridge would fail entirely. That is precisely why, despite billions of dollars of investment, we see capacities just hovering around 100 to 150 qubits per chip. We are bottlenecked by the plumbing.
So IBM and Google are effectively building these incredibly exquisite, fragile glass chandeliers. But they have to hang them inside these massive, energy-devouring freezers.
Yeah.
And every time they want to add just one more light bulb to the chandelier, they have to run another thick copper extension cord through the freezer door, which inherently lets the cold out. It's a self-defeating scaling model.
It is entirely self-limiting. And to make matters worse, even when they perfectly balance the cooling and the wiring, the coherence times, like the duration that the qubit actually survives in its quantum state before collapsing into noise, are agonizingly short.
How short are we talking?
We are looking at microsecond scale coherence, between roughly 50 and 400 microseconds for the absolute best physical qubits on these platforms.
Microseconds, millionths of a second.
Yep.
You have a fraction of a blink of an eye to initiate your algorithm, run the calculations, and run the data before the universe just forces the information to evaporate.
Exactly.
Which makes the quantum lattice counterproposal so arresting. Because this white paper doesn't just offer an incremental improvement, it literally throws the entire dilution refrigerator paradigm into the trash.
Totally discards it.
They aren't proposing 150 qubits on a chip. They are outlining a path to up to 1 million qubits per square centimeter. They aren't settling for microsecond coherence. They're targeting 100 to 500 milliseconds.
Half a second.
That is half a second. And the kicker, The claim that makes this whole thing sound like literal science fiction is the potential for near-room temperature operation.
That is the claim that forces you to sit down and read the paper twice.
Yeah.
And to understand the mechanism behind how they actually plan to achieve this, you have to look closely at the material science.
Okay, let's dig into that.
Why are superconducting systems so bulky and noisy in the first place? It comes down to how they are manufactured. IBM and Google rely heavily on what we call hetero-interfaces.
Hetero-interfaces.
Yeah, meaning they are taking fundamentally different elemental materials and forcing them together. Usually you have a silicon or maybe a sapphire substrate, and you are depositing microscopic circuits of aluminum or niobium on top of it.
And, at the human scale, that just looks like a perfectly smooth, shiny computer chip.
Mm.
But at the atomic scale, hetero meaning different, and interfaces meaning the boundary where they touch, that boundary is where the nightmare happens.
It is a chaotic war zone. When you force the crystalline atomic lattice of silicon to press up against the crystalline lattice of aluminum, the atoms don't match up perfectly.
Because they're different sizes.
Exactly, the spacing is different. So you get atomic bonds that have nothing to connect to, what chemists call dangling bonds. You get stray electrons that get stuck in these microscopic crevices. This mismatch creates what quantum physicists call two-level system noise, or TLS noise, along with charge traps.
So because you're essentially gluing two different metals together, the atomic glue joint itself acts like this buzzing, erratic electric field that constantly bumps into the qubit and destroys its delicate state.
Right.
The materials are basically fighting each other.
That's a great way to conceptualize it. The boundary itself generates the decoherence. Now, look at the radical design philosophy of the quantum lattice.
Material monolithism.
Yes, material monolithism. The proposal is that every single functional layer of the entire computer, so the qubit itself, the logic gates that control it, the internal wiring, the classical feedback systems, and the structural scaffolding, is synthesized from a single continuous material family.
The graphene thing.
The graphene family.
Yeah.
It is pure carbon from top to bottom, zero non-carbon elements, zero non-carbon interfaces.
So instead of building a computer out of 100 different elemental puzzle pieces just glued together, we are taking one continuous, uniform, diamond-like material and carving the different components directly into its internal structure. Because there are no mismatched materials, there are no atomic war zones.
Yeah.
You eliminate the TLS noise completely.
Exactly. You eliminate the boundaries, you eliminate the noise. But as you pointed out, we have to look closer to see how they pull this off. Saying we'll just use pure carbon sounds great on a macro level, but we have to drill down to the atomic level.
Right.
If we aren't using superconducting loops of aluminum to hold our quantum information anymore, what is the actual qubit? How do you force a literal chunk of carbon to hold a superposition?
Right, because my pencil lead isn't currently calculating the secrets of the universe while sitting on my desk. What makes their carbon so special?
The foundational building block of this architecture is the graphene quantum dot, or GQD. The paper specifies a 3 to 5 nanometer region of graphene configured as a hybrid spin-valley charge qubit.
Okay, let's scale that for the listener. 3 to 5 nanometers is almost incomprehensibly tiny.
It really is.
A single strand of human DNA is about 2.5 nanometers across. So we're talking about isolating a cluster of carbon atoms, roughly the width of maybe 2 DNA strands.
Yes.
But going back to the material choice, is there an inherent quantum advantage to using carbon beyond just avoiding those mismatched hetero interfaces?
There is a massive fundamental advantage, and it has to do with the nucleus of the atom. In the fight against quantum decoherence, one of the most insidious enemies is nuclear spin.
Okay.
Most atomic elements have a nucleus that naturally spins, which generates a microscopic magnetic field. If your incredibly sensitive qubit is sitting inside a material where billions of neighboring nuclei are spinning and generating their own tiny random magnetic fields, the qubit just gets completely overwhelmed.
It's like trying to perfectly tune a delicate violin while sitting in the middle of a stadium full of screaming sports fans.
Oh, that's a perfect analogy.
The background magnetic noise is deafening.
Spot on. The magnetic interference crushes the quantum state. But carbon changes the game completely. Natural carbon found on Earth is composed overwhelmingly of the carbon-12 isotope, about 98.9%. And by a beautiful quirk of nature, carbon-12 has a nuclear spin of exactly 0.
Wow, it doesn't spin at all. So the stadium is dead silent.
It is entirely magnetically silent. It provides an intrinsically pristine matrix for quantum operations. Furthermore, carbon is a very light element. It has a low atomic mass.
Right.
Because of this lightness, its spin-orbit coupling is exceptionally weak, roughly 3 orders of magnitude smaller than what you see in heavier semiconductor materials like silicon or gallium arsenide.
Okay, pump the brakes. Spin-orbit coupling. We try to break that down. Is that basically a measure of how much an electron's internal spin, which we might be using to store our ones and zeros, is dragged around or influenced by its physical motion as it orbits the nucleus?
You've got it exactly. In heavy elements, if the atom vibrates or the electron shifts its orbit, that physical movement heavily influences and flips the electron's spin state. They are tightly coupled together.
Okay.
But in light elements like carbon, the spin is highly decoupled from the physical motion. The atom can vibrate, but the electron spin just ignores it and stays perfectly stable.
That's convenient.
But honestly, the real conceptual breakthrough of this specific graphene architecture isn't just relying on electron spin. It's their utilization of what are called valley states.
Yes. This is a massive focus of the white paper. Valley hybrid coherence. When I hear the word valley, I naturally picture a physical valley between two mountains. Are we talking about a physical shape in the carbon?
Not physical space, no. We are talking about momentum space.
Momentum space.
Yeah, and this can be a tricky concept, but let's just use an analogy. Imagine the energy landscape of graphene's crystalline honeycomb structure as a sprawling topographical map.
Okay, I have a map in my head.
On this specific map, electrons naturally want to settle into the lowest energy points. In graphene, the geometry of the lattice creates 2 distinct, incredibly deep, separate craters or valleys on this map where electrons prefer to sit. Physicists label them the K and K prime valleys in the Brillouin zone.
Okay, so if I drop an electron onto this momentum map, it's basically going to roll down the hill and settle into either the K valley or the K prime valley.
Correct. And here is the absolute magic of this. These 2 valleys are separated by a massive distance in momentum space.
Meaning they're far apart on our map.
Exactly. It takes an enormous, highly specific injection of energy, like a massive kick-to force an electron to climb out of the K valley, travel all the way across the high-energy mountain range, and drop into the K prime valley.
Oh, I see.
Because they are so deeply isolated from one another, if you encode your quantum information into the valley degree of freedom, meaning a 0 is the electron being in the K valley, and a 1 is the electron being in the K prime valley. That information is phenomenally robust.
Because it's locked in the crater.
Yeah.
Random thermal noise or slight vibrations just don't have enough energy to kick the ball over the mountain.
Exactly.
And the paper backs this up with some absolutely jaw-dropping metrics.
They do. They cite recent empirical experiments utilizing gate-defined bilayer graphene dots, the valley relaxation times, so the time it takes for the electron to just randomly flip valleys, which physicists denote as T1 exceed 500 milliseconds.
Half a second. Again, compared to the 50 to 400 microseconds that the incumbent superconducting giants are currently achieving, that is an eternity.
It is a foundational shift in stability.
Yeah.
But they take it even further. When they actively lock the electron spin state together with its valley state, creating what quantum mechanics refers to as a spin-valley-Kramers pair, the relaxation time just skyrockets.
Yeah.
It approaches an absurd 38 seconds at 30 millikelvin.
38 seconds.
Yeah.
A quantum state surviving for 38 seconds is almost difficult to believe.
It really is.
In a world where calculations take millionths of a second, 38 seconds gives you time to run complex algorithms, check them, run them again, and go grab a cup of coffee before the qubit even starts to degrade.
It completely changes the error correction math, and they achieved greater than 99% single-shot readout fidelity for these states at near-zero magnetic field.
Yeah.
But, you can't just have an isolated qubit. You have to be able to control it.
Right, which brings us to the math, and I want to pause here because the white paper actually includes the specific effective Hamiltonian equation for this qubit system.
Yes, it does.
And while I don't want to just read a string of Greek letters over audio, I notice the equation is beautifully segmented. It defines the energy landscape of this dot. Can we conceptually break down what this Hamiltonian is actually describing?
We can absolutely do that without getting bogged down in the syntax. So, a Hamiltonian is simply the mathematical master equation that defines the total energy of a quantum system and dictates how it evolves over time.
Okay.
The equation in the paper is split into 3 core components. The first component represents the spin-orbit splitting. That's the baseline energy foundation related to whether the electron's spin is pointing up or down.
Okay, so that's the spin foundation. What's the second piece?
The second component describes the valley splitting. This dictates the energy gap between those 2 deep craters we talked about, the K and K prime valleys. And crucially, the paper notes a specific variable here indicating that this valley splitting is gate tunable.
Meaning we, as the operators, have a mechanism to artificially change the depth of the shape of those valleys on demand.
Exactly. Which brings us to the third and most important component of the Hamiltonian, the electrostatic gate pulse. This is our control knob. By applying a highly specific voltage pulse over a specific duration of time, you can mediate charge-based operations.
But wait, I have to challenge this logic for a second. We just spent all this time establishing that these valley states are incredible because they are perfectly isolated, right?
Yes.
They are tucked away in these deep momentum craters where no random noise can touch them. That's why they survive for 38 seconds. So if they're so perfectly isolated, how is it physically possible for us to talk to them or manipulate them without instantly breaking that isolation and causing decoherence?
It is a brilliant paradox, and it's really the core genius of the hybrid spin-valley charge qubit. The Kramer's doublet, that locked spin-valley state we just mentioned, provides the system with what physicists call topological immunity against single-channel decoherence.
Okay, let's unpack that.
Sure, so if a random piece of thermal noise or a stray magnetic field hits this qubit, the noise might try to flip the electron's spin, or it might try to bump the electron into the other valley. But random noise is inherently uncoordinated.
Right, it's just random.
Exactly. It cannot perfectly do both at exactly the same time with the precise energy required. Because the spin and the valley are mathematically locked together, the state simply ignores the random single-channel noise.
So it's like a bank vault that requires two separate keys to be turned at the exact same millisecond.
Precisely.
A random burglar bumping into the door or just picking one lock does absolutely nothing. The vault stays sealed.
That is a phenomenal analogy. The vault stays sealed against random noise, but we have both keys. And our double key is that electrostatic gate pulse. We aren't relying on noisy magnetic fields to flip the spin. Instead, we use a perfectly tuned electric charge delivered through the carbon wiring. We use that charge to gently, artificially tilt the entire momentum energy landscape. We temporarily lower the mountain between the two valleys, smoothly slide the electron over to the other side to change its state from a 0 to a 1, and then instantly raise the mountain back up.
Wow.
We use the charged degree of freedom to safely talk to the isolated valley degree of freedom.
That is unbelievably elegant. You just tilt the board, roll the ball into the other crater, and lock it back down.
Exactly.
Okay, so we have established this hyper-stable, magnetically silent carbon qubit. But a single 3-nanometer speck of pure carbon-12 can't just float in a void. We have to physically place billions of these dots somewhere, wire them together, and protect them from the outside world.
They need a home.
Right. Which leads us to the most visually striking part of this entire proposal, the graphene aerogel matrix.
Right. A qubit is conceptually useless if you can't embed it into a manageable physical architecture. The white paper proposes that instead of laying these dots out on a flat, 2D silicon wafer, they will be volumetrically embedded inside an ultralight 3D scaffold made entirely of graphene aerogel.
And when the paper says ultralight, I mean, they are pushing the boundaries of solid matter here. Yeah. The specified density of this aerogel is between 0.001 and 0.1 grams per cubic centimeter.
It's incredibly light.
I ran the numbers on that. At its lower bound, this solid material is roughly 6 times lighter than the ambient air you are breathing in the room right now.
Yeah.
It is essentially a ghost. It is a solid made of nothing.
It is predominantly empty space. Structurally, it is a hierarchical matrix of microscopic pores, with the voids ranging from 10 to 100 nanometers across. And it is precisely this extreme porosity that unlocks its ultimate superpower thermal and mechanical isolation. Think back to the dilution refrigerator problem, the thousands of metal wires leaking heat down to the quantum chip. We need materials that stop heat dead in its tracks. The thermal conductivity of this graphene aerogel is recorded at an astonishingly low 0.005 to 0.03 watts per meter Kelvin.
A contrast, what is the thermal conductivity of a normal solid sheet of dense graphene?
Bulk graphene is actually one of the best thermal conductors ever discovered. Its thermal conductivity sits around 5,000 watts per meter Kelvin.
So by puffing it up into this sponge, we are dropping the thermal conductivity from 5,000 down to 0.005.
A millionfold reduction.
The heat simply cannot navigate the maze of the sponge.
It can't. But it's not just macroscopic ambient heat we are worried about here. We are deeply concerned with specific quantized vibrational heat. This brings us to a massive section of the paper phonon suppression.
Okay, we need to deep dive into this
Yeah.
because I think most people have heard of a photon, right? A fundamental particle or packet of light energy. But what exactly is a phonon?
A phonon is a quasi-particle. It is a quantized unit of vibrational energy. If you think about the atomic lattice of any solid object, a piece of metal, a diamond, a table, the atoms are connected by chemical bonds that act like tiny springs. If one atom gets slightly warm, it jiggles.
Makes sense.
That jiggle pulls on the spring, which yanks the neighboring atom, which yanks the next one. This creates a microscopic propagating wave of mechanical vibration. It's essentially a microscopic earthquake or a silent sound wave traveling through the solid. That wave is a phonon.
And if that microscopic earthquake travels through the chip and hits our delicate little valley state electron.
It violently shakes the energy landscape. It provides that random kicks that knocks the electron right out of the valley crater.
Right.
Instant decoherence.
Wow.
This is the primary physical reason why traditional quantum computers have to be cooled down to 15 millikelvin. They are literally freezing the atoms in place to kill off the phonons. They cannot allow the lattice to jiggle.
So how does a gossamer sponge of carbon stop a microscopic earthquake?
It comes back to the hierarchical air-filled nanopore structure. The aerogel is constructed from ultra-thin atomic graphene sheets interconnected by slightly denser carbon struts. When a phonon, a vibrational wave, tries to propagate through this material, it doesn't have a solid path.
It is mostly air.
Exactly. It travels a few nanometers, hits the edge of a pore, hits empty air, and reflects back on itself. The physical, chaotic, void-filled structure of the sponge violently scatters, dampens, and dissipates the vibrations. The phonons are physically bottlenecked and trapped in the outer layers. They literally cannot reach the embedded quantum dots deep inside the matrix.
I see exactly what they're doing. It's like taking a delicate ringing bell and wrapping it in miles and miles of advanced acoustic studio foam.
Yes.
It doesn't matter how loud the construction work is outside the building. The sound waves hit the complex geometry of the foam, bounce around the air pockets, lose their energy, and never reach the bell.
That is a phenomenal way to visualize it. It's acoustic foam for quantum mechanics. And there's a secondary, equally massive benefit to all these microscopic air pockets. They act as native, built-in dielectric spacers.
Dielectric, meaning they act as an electrical insulator to prevent short circuits.
Yes. In traditional 2D quantum chips, you have incredibly tiny, exquisitely sensitive wiring running very close together. Whenever you run an electrical signal down a wire, it generates an electromagnetic field.
Right.
To prevent that field from bleeding over and interfering with the wire next to it, a problem called crosstalk, you have to physically coat the wires or separate them using foreign insulating materials like silicon dioxide.
Oh, I see where this is going.
But as we established earlier with heterointerfaces, the moment you introduce a foreign material like oxygen or silicon into the matrix, you introduce dangling bonds, charge traps, and TLS noise.
Oh, this is brilliant. In the aerogel matrix, the conductive carbon wires are separated by absolutely nothing.
Nothing at all.
Just the empty void of the nanopore. And a vacuum, or pure empty air, is a perfect electrical insulator. You get perfect dielectric isolation without having to paint your delicate quantum wires in noisy, chaotic plastic or oxide coatings. It solves the insulation problem by simply removing the material entirely.
It is designed by subtraction. The structural voids of the sponge provide mechanical phonon decoupling, extreme thermal insulation, and perfect dielectric isolation all simultaneously, and all without introducing a single non-carbon atom into the device.
Okay, so we have theoretically designed the perfect pure carbon qubit, and we have placed it inside the perfect ultra-insulating acoustic foam carbon sponge.
The physics checks out.
The theory is beautiful, but we have reached the massive elephant in the room. A beautiful theory on a whiteboard is completely useless if human engineering cannot physically build the thing.
Very.
How in the world do you construct a microscopic 3D matrix of empty air and perfectly embed 3-nanometer dots inside of it without using a multi-billion-dollar semiconductor fabrication plant?
Yeah.
Because, IBM is using massive 300-millimeter clean-room silicon fabs. How do you make a quantum sponge?
You've hit the exact transition point where this paper moves from theoretical physics to a true manufacturing miracle. They outline an entirely novel fabrication pipeline called maskless single-step femtosecond laser direct writing. In the literature, it's abbreviated as SSLDW.
Maskless. Let's define what we're replacing here.
Yeah.
In traditional classical computer manufacturing, like making the processor in my smartphone, they use masks, right? It's photolithography.
Exactly.
You shine ultraviolet light through a complex stencil to etch a pattern into silicon.
And it's an incredibly arduous planar process. You need extreme vacuum chambers, toxic chemical etchant with photosensitive resists, and you have to do it layer by painstaking layer. The quantum lattice proposal throws the entire concept of lithography away. The entire 3D device is fabricated through a sequential, laser-only volumetric pipeline. No stencils, no chemicals, no vacuums, just highly tuned lasers hitting a raw precursor material.
Let's talk about that precursor material. What are we actually shooting the lasers at? Because the paper mentions starting with graphene oxide, which sounds highly technical, but then it also explicitly mentions utilizing bio-derived hemoglobin powder, as in the protein in blood.
It really does read like science fiction, I know, but yes, hemoglobin. While graphene oxide is the standard, hemoglobin is actually incredibly rich in tightly bound carbon structures.
Wait, really?
Yeah. In recent advanced materials literature, laser pyrolysis of hemoglobin has been proven as a highly sustainable, wildly effective carbon precursor for electronics.
No.
So the process begins by taking this hemoglobin powder or the graphene oxide dispersion and mixing it into a simple water solution along with a bit of ascorbic acid, which is literally just vitamin C.
Vitamin C. What is the vitamin C doing in our quantum computer?
It acts as a mild, environmentally friendly chemical reductant. It helps begin the process of stripping oxygen away from the carbon lattice. They take this aqueous mixture, they sonicate it, meaning they blast it with high-frequency sound waves to ensure it is perfectly homogeneously mixed at the molecular level, and then they rapid freeze it using liquid nitrogen inside simple silicone molds.
So the very first step of building a next-generation quantum supercomputer is basically freeze-drying a mixture of blood protein and vitamin C into a little solid hockey puck.
That is precisely what it is. That frozen, freeze-dried puck is the precursor monolith. It's
Yeah.
highly porous but unrefined.
Okay.
To transform it, they introduce the two-laser system. First, they hit this puck with a continuous wave CO2 laser or an infrared fiber laser. This is the pyrolysis step.
Pyrolysis, so burning it.
Essentially, yes. As the broad laser beam washes over the precursor, it rapidly superheats and graphitizes the material in a matter of seconds. It drives off the remaining oxygen and water, and the material rapidly puffs up into that ultralight hierarchical graphitic aerogel we talked about. By tuning the speed and power of the CO2 laser, they dictate the exact density and pore size of the sponge.
So the first laser is a blunt instrument. It basically bakes the cake. It turns the solid chemical puck into the empty 3D sponge scaffolding.
Correct. But right now, it's just a highly structured, dumb piece of foam. It contains no information. To make it a quantum computer, we need the second laser. And this is where the absolute magic happens.
Okay.
They utilize a femtosecond laser, specifically one operating at a 780 nanometer wavelength, firing incredibly short pulses that last only 100 to 500 femtoseconds.
We need to pause on the word femtosecond.
It's fair.
A microsecond is a millionth of a second. A nanosecond is a billionth. A femtosecond is 1/1,000,000th of 1/1,000,000th of a second. It is a duration of time so fleeting that light itself, which can travel around the Earth 7 times in a second, barely moves a fraction of a millimeter in a femtosecond. Why do we need a laser to pulse that fast?
Because of the physics of thermal energy transfer.
Yeah.
If you shine a normal continuous laser into a delicate carbon sponge, the material absorbs the light, it heats up, it melts, and it just burns away.
Makes sense.
But a femtosecond pulse is so incomprehensibly fast that it delivers a massive violent spike of peak optical power without actually having the time to transfer macroscopic heat to the surrounding lattice.
Oh, wow.
It utilizes multiphoton absorption. It acts like an invisible, microscopic, three-dimensional scalpel. The laser beam easily passes through the transparent voids of the aerogel, focusing at a precise point deep inside the volume of the sponge. Wherever that focal point hits, it instantly ablates and reduces the carbon atoms, violently rearranging them. The carbon atoms are forced to cool and nucleate in microseconds, forming those precise 3 to 5 nanometer graphene quantum dots right in the middle of the empty air pores.
Okay, I have to push back here.
Go for it.
Because this sounds amazing, but the engineering tolerances we are talking about are ridiculous. They literally want to 3D print a quantum computer inside a sponge. They're shooting a laser through a foamy material and just hoping that the focal point ablates the exact right cluster of atoms to perfectly form a 3 nanometer Valley State qubit.
Right.
How could they possibly ensure the dot is perfect? If the resulting quantum dot is 4 nanometers instead of 3, the shape of the momentum valleys changes, the energy equation breaks, and the qubit is totally useless.
You've identified the single greatest engineering hurdle of the entire proposal. The potential for defect generation is immense, but the white paper outlines two critical, highly advanced mitigation strategies to enforce structural perfection during the writing process.
What are they?
First, they utilize electric field assistance. While the femtosecond laser is writing inside the sponge, the system applies a strong, highly calibrated external electric field across the entire aerogel matrix.
What does an electric field do to a newly ablated carbon atom?
It acts as an invisible directional mold. As the laser blasts the carbon, the atoms briefly become highly energized and mobile. Before they can settle randomly, the electric field physically grabs the temporary dipoles of the carbon structures and forces them to align.
Whoa.
Yeah, it physically guides the carbon atoms as they cool and reform, strongly promoting the symmetric bilayer-like stacking configuration that is absolutely necessary to create the spin-valley-Kramers pair.
That's incredible. So the laser provides the chaotic energy to melt the carbon, but the electric field acts like a magnetic stencil, forcing the atoms to snap into the correct crystalline grid as they solidify.
Exactly. And the second, even more impressive technique is real-time photoluminescence monitoring, or PL feedback.
How does that work?
As the femtosecond laser strikes the carbon and forces a quantum dot to form, that newly born quantum dot instantly fluoresces. It emits a very specific frequency of blue light. The manufacturing system is equipped with ultrafast photodetectors that monitor the exact spectrum of this blue light in real time.
So, as the laser writes the dot is shining light back at the laser.
Yes. And the exact wavelength of that blue light is directly correlated to the physical size and valley structure of the quantum dot. If the light shifts slightly red or slightly blue, the manufacturing system instantly knows that the dot is forming at the wrong size.
That's genius.
And here's the best part. It doesn't wait until the process is over. Because the femtosecond laser operates in a train of pulses, the optical feedback loop can analyze the blue light from pulse number 1 and instantly adjust the intensity or duration of pulse number 2 before the dot has even finished cooling.
That is wild. It's essentially listening to the voice of the qubit like the light it emits as it's born to, continuously sculpt it until it's perfect. And it does this continuously for the entire internal lattice.
It does it for the entire volumetric structure. Because as the femtosecond laser continuously scans through the 3D volume of the sponge, it isn't just creating the isolated qubits. It also selectively graphitizes the struts of the aerogel between the qubits to create the conductive graphene wiring and those electrostatic gates we talked about.
Wow.
And remarkably, as the laser moves to the outer periphery of the sponge, it alters its pulse pattern to write classical graphene field effect transistors, or FETs, directly into the carbon shell.
Wait. It is printing classical, traditional computer chips onto the outside shell of the quantum computer chip at the exact same time using the exact same laser.
In a single, uninterrupted volumetric sweep. The core qubits in the center, the 3D control wires routing between them, and classical feedback processors acting as a protective shell on the outside, all carved out of the exact same continuous block of carbon.
You know, knowing this manufacturing process really reframes their production timeline, which when I first read it seemed impossibly arrogant.
Oh, the 14-day sprint.
Yeah. The paper outlines a 14-day sprint to go from raw hemoglobin powder to a fully functioning 4 to 8 qubit proof-of-concept device.
The 14-day timeline is absolutely designed to shock the incumbent industry. Day 1 is entirely dedicated to precursor synthesis and CO2 laser pyrolysis, making the aerogel puck. Days 3 through 5 are spent dialing in the femtosecond laser loop, specifically checking that blue photoluminescence feedback to ensure they are consistently hitting over an 80% monolayer yield for the quantum dots.
Right.
Days 8 through 10 are the actual rapid-fire writing of the prototype arrays, and by day 14, they intend to demonstrate a working hybrid quantum classical feedback loop on the chip. But the real paradigm shift is what they outlined for week 3.
Yes. The transition to roll-to-roll continuous production. Let's really explore this, because they are talking about treating the manufacturing of the most advanced technology on Earth, like the printing presses at an old newspaper factory.
It is the ultimate logical conclusion of maskless laser writing. If you don't require extreme vacuum chambers and you don't require painstaking layer-by-layer silicon stenciling, you don't need a clean room.
Right.
You can simply apply your flexible carbon precursor material onto a massive moving spool of flexible substrate. You mechanically unroll it, feed it continuously under a wide-beam CO2 pyrolysis laser to instantly puff it into an aerogel ribbon, and then feed that ribbon directly beneath an array of hundreds of parallel femtosecond lasers.
It's just moving along a conveyor belt.
Exactly. And these lasers rapid-fire the qubit lattices, the wires, and the classical processors volumetrically into the moving tape.
The paper literally brands them quantum tapes. They envision meter-long ribbons of aerogel containing 10,000 pristine physical qubits per square centimeter. And the scaling model completely bypasses the limitations of silicon wafers.
Completely.
If you want a more powerful quantum computer, you don't have to redesign a bigger, denser chip. You just take the tape off the spool, cut it into squares with a laser, and stack them vertically like modular 3D building blocks. The femtosecond lasers can even weld the conductive interconnects between the stacked layers.
The industrial implications are just staggering. The capital expenditure bottleneck completely shifts. Instead of a tech giant needing to raise $2 billion to build a new semiconductor fabrication facility, a startup could theoretically buy a bank of million-dollar femtosecond lasers and a school of precursor and begin printing quantum volume. It entirely democratizes the hardware scaling model.
Okay, this is all breathtaking engineering, but let's pump the brakes and move into the practical reality of running these machines, because we have to address error correction and real-world commercial power.
The practical stuff.
Right. Sure, we can theoretically print massive meter-long spools of quantum tape with millions of Valley-Steak qubits embedded in them.
Yeah.
But quantum systems are famously notoriously error-prone. We mentioned Google's surface codes earlier.
Yeah.
If we have a million qubits, but random environmental noise is constantly causing them to make microscopic calculation errors, the computer is utterly useless. It just produces extremely fast garbage. How does this carbon architecture handle the mathematical noise, especially without needing those thousands of coaxial cables to route the error signals to a massive external supercomputer?
The error correction strategy presented here relies on two massive intertwined innovations. First, the native physical 3D geometry of the aerogel lattice allows them to utilize what are called QLDPC codes, quantum low-density parity check codes.
I know IBM has been looking into LDPC codes as well. How do they fundamentally differ from the surface codes that Google is currently championing on their Willow chip?
Surface codes are brilliant and highly effective, but they suffer from a massive resource strain. They are a 2D topological code. For every one logical qubit, which is a mathematically perfect error-free qubit ready to run an actual algorithm, a surface code architecture might require up to 1,000 physical qubits surrounding it just to act as dedicated error checkers.
1,000 to 1.
Yeah, it's an immense overhead constraint. You build a 1,000 qubit machine, and you only get one usable qubit out of it. QLDPC codes, fundamentally, are mathematically far more intertwined and efficient. They utilize complex parity checks that allow multiple qubits to check each other simultaneously.
Wow.
Mathematically, they require roughly 90% less overhead than surface codes to achieve the exact same level of logical protection.
90% less overhead. So instead of needing 1,000 physical qubits, babysitting one logical qubit, you might only need 100 or even fewer.
Exactly. The math of LDPC is vastly superior. But here is the massive catch: QLDPC codes are notoriously practically impossible to wire up on a traditional flat 2D silicon chip.
Why is that?
Because the mathematics of LDPC require highly complex non-local connections. A physical qubit on the left side of the chip needs to perfectly connect to a physical qubit on the far right side of the chip and simultaneously to one in the middle. On a flat 2D plane, you physically cannot route those wires without them crossing over each other.
And in quantum.
And in quantum mechanics, if two wires cross, their electromagnetic fields interact. You get crosstalk, you get noise, and the system fails.
But the quantum lattice isn't a flat 2D plane. It is natively a 3D sponge.
Precisely. Because you have a full volumetric space, the femtosecond laser can route the electrostatic graphene gate struts in true three-dimensional space. The qubits can communicate with each other vertically, horizontally, diagonally, and around corners without the conductive pathways ever physically intersecting.
That's so smart.
The physical 3D aerogel is the absolute perfect host for the complex topology of QLDPC mathematics.
That is a beautiful synergy of hardware and software.
Yeah.
Wait, even with the most efficient math in the world, the computer still has to actively process those errors.
Right.
In Google and IBM's current systems, when an error occurs, they have to read the error state of the qubit, send that weak microwave signal all the way up the copper coaxial cable, out of the 15 millikelvin dilution refrigerator into a room temperature classical supercomputer rack sitting next to the fridge.
Yeah, a huge round trip.
The classical computer calculates the exact microwave pulse needed to fix the error and sends that pulse all the way back down the cable to correct the qubit before it fully decoheres. That input-output round trip is a massive, incredibly slow bottleneck.
And that bottleneck is completely obliterated by the second massive innovation on chip classical feedback. Remember those classical graphene field effect transistors and memristors that the laser wrote onto the outer peripheral shell of the aerogel sponge?
The classical computer processors literally baked into the carbon crust of the quantum sponge.
Exactly. Those classical graphene circuits are specifically designed to be the error checkers. They dynamically extract the error syndromes from the quantum core, perform the QLDPC parity calculations, and apply the electrostatic correction voltages locally right there within the carbon matrix, just microns away from the qubits.
Oh, wow.
The error signals never have to leave the chip. They never travel up a wire to an external computer. This entirely eliminates the crippling input-output latency that is currently choking superconducting platforms.
So, synthesizing this, we have a chip that fixes its own errors instantaneously using built-in classical processors, requires virtually no external wiring, and physically supports the most mathematically efficient error correction codes known to physics.
That's the dream.
And this naturally leads us directly into the commercial advantages. Because if you truly eliminate the dilution refrigerator, you aren't just saving a few megawatts on your electricity bill, you are fundamentally changing where a quantum computer is allowed to physically exist in the world.
The white paper places a heavy emphasis on swap size, weight, and power. To move a standard dilution refrigerator, you need a forklift, you need access to industrial power lines, and you need a dedicated facility.
Right.
But because of the aerogel's extreme phonon suppression and the carbon-12's lack of nuclear spin, this quantum lattice platform targets near room temperature operation. Even if the physics eventually mandate mild cryogenic cooling, say, dipping the tape in liquid nitrogen, which operates at 77 Kelvin and costs roughly the same as milk, it completely revolutionizes the swap profile.
Think about what this means in practical terms. It is the historical equivalent of transitioning from a 1960s ENIAC vacuum tube mainframe that took up an entire university basement to a modern laptop that you can just slide into a messenger bag.
Exactly.
The paper explicitly lists practical applications for low-swap quantum hardware. What industries get disrupted first by this?
Defense and aerospace are the immediate adopters. Imagine deploying a modular room-temperature quantum computer onto a submarine, or integrating it into the avionics of a fighter jet. You could run highly complex real-time logistical optimizations or crack advanced encryption algorithms right on the battlefield without needing a satellite uplink to a server farm.
That's huge.
But beyond pure computing, there is a massive application in quantum sensing.
Quantum sensing. So using the qubits not to calculate,
Right.
but to actually feel the environment.
Exactly. Because qubits are inherently agonizingly sensitive to environmental changes, which is usually the exact problem we are trying to solve, you can harness that sensitivity. A tiny, portable array of these highly stable valley-state qubits could act as the most extraordinarily precise magnetic field sensor or atomic clock in human history.
Oh, I see.
You could mount them on drones for deep earth mineral and oil exploration, mapping subterranean magnetic anomalies with pinpoint accuracy. Or use them for ultra-precise, unjammable navigation in environments where GPS signals are denied or blocked.
And there's the biomedical aspect too, right? The molecular simulation potential.
That is perhaps the most globally impactful application. Accurately simulating how complex proteins fold or how novel chemical catalysts interact at the atomic level is exponentially too difficult for classical computers. It would take a supercomputer thousands of years to perfectly simulate a large molecule.
Because there's too many variables.
Right. But quantum computers operate natively, using the same quantum mechanics that govern the molecules. They simulate it naturally. If you have a room temperature quantum module that can just sit on a pharmacologist's desk, it democratizes drug discovery. You don't need to rent million-dollar time slots on IBM's cloud mainframe. You just run the molecular simulation locally on your carbon sponge to find the cure.
It's a total paradigm shift for the entire technological market.
Ah.
It's breathtaking. But, you know, this is where things get genuinely surreal.
Yeah, they do.
Because the authors of the white paper could have easily stopped right there. They could have published the engineering for a room temperature, 3D printable, self-correcting quantum computer, demanded a Nobel Prize, taken their venture capital, and retired.
They really could have.
But they didn't stop there. The final section of this technical document takes a hard, staggering pivot. It gets incredibly weird, highly theoretical, and deeply philosophical about the foundational nature of the universe itself.
Yes, we have to discuss the mind-bending physics implications section. The authors delve deeply into what they have titled the quantum lattice framework for reality.
Okay.
They propose that the architecture they are physically building, this three-dimensional, interconnected network of discrete quantum information nodes inside the aerogel, isn't just a powerful calculator. They argue that the math running this sponge perfectly models space-time and gravity as emergent properties of a discrete, information-rich manifold.
Okay, we need to take this very, very slowly.
I know, it's a lot.
Because we are leaving engineering and entering quantum gravity. Are they actually suggesting that space and time, the literal physical fabric of the universe that you and I currently exist in, is structurally identical to their carbon sponge?
Mathematically speaking, yes, that is their exact assertion.
Right.
Let's break down what they call the kinematic foundation.
Right.
In classical Newtonian physics, we naturally think of space as a smooth, continuous, empty box. And matter stars, planets, you and me, is just the physical stuff placed inside that smooth box. But in this quantum framework, they entirely discard the continuous box. They model the universe as a complex mathematical graph. Think of a massive 3D net or a woven grid. Mathematically, it's defined as G, V, E, where V represents vertices or discrete nodes, and E represents the edges or the mathematical connections between those nodes.
So space itself isn't a smooth emptiness. Space is pixelated.
Yes.
It is constructed of tiny, discrete, individual nodes operating at the absolute smallest scale of physics, the Planck scale.
Exactly. The universe is a lattice of pixels, and the stuff inside the universe, the reality we experience, is defined entirely by the state of information at each of those nodes. It is defined by the entanglement and the information density.
This is wild.
Matter isn't a solid object. Matter is just a highly dense concentration of quantum information existing on these nodes. Now, to explain how these nodes interact, the authors introduce a mathematical operator called the graph Laplacian.
I'm going to need an analogy for the graph Laplacian. How does it work?
The graph Laplacian, mathematically written as L equal dA, is an operator that dictates the tension or the relational dynamics of this informational fabric.
Okay.
In classical physics, a Laplacian operator describes how things diffuse, like how heat naturally spreads out uniformly across a flat metal plate. In this quantum lattice framework, the graph Laplacian describes how information or energy naturally propagates or pulls from one discrete node to its interconnected neighbors.
Okay, give me a visual.
Think of the universe as a massive, tightly woven trampoline. If you push down heavily on one specific node, the graph Laplacian is the mathematical rule that dictates exactly how all the surrounding nodes in the web are pulled down and stretched along with it.
Okay, so if the universe is a tightly woven trampoline made of informational pixels, how do they explain gravity? Because the boldest claim in this paper is that gravity is not a fundamental force, but merely a geometric consequence of how information is distributed.
This is where the physics gets profoundly beautiful. They map von Neumann entropy, which is a strict mathematical measure of quantum information complexity, entanglement, and disorder, directly to the physical property of mass. In this specific model, mass is not an arbitrary inherent physical constant. A proton isn't just intrinsically heavy. Mass is strictly a measure of localized entropy gradients.
Wait, mass is just complexity. So an atom or a massive planet or a human being isn't fundamentally made of heavy stuff. We are just highly complex, incredibly dense traffic jams of information on the quantum grid.
Yes, you are a dense cluster of quantum information, and because you are such a dense, tangled knot of data, you create drag or tension within the surrounding lattice. The graph Laplacian dictates that this massive knot of information must pull tightly on the surrounding empty nodes of the graph. That pull, that tension field propagating outward through the discrete geometric grid, naturally and mathematically converges to the classical inverse square law when viewed from a macroscopic distance.
The inverse square law. That is literally Isaac Newton's foundational law of gravity.
Yes, it is.
The law stating that the gravitational pull between two objects gets weaker the further away they get.
Yeah.
Exactly proportional to the square of the distance between them.
Exactly. What the authors have done is mathematically prove that if you start with absolutely nothing but discrete pixels of quantum information interacting on a grid and apply the rules of entropy, the mathematics naturally and unavoidably produce Newtonian gravity on a macro scale.
That is mind-blowing.
Gravity is not an external, mystical pulling force acting on solid matter. Gravity is simply a structural, geometric necessity of an information-centric universe trying to balance its own tension.
I want to make sure I fully grasp the magnitude of what they're doing here. By physically constructing this 3D quantum aerogel sponge, by carefully placing discrete quantum dots in a lattice and linking them with information. They aren't just making a computer to solve math problems.
No, they aren't.
They're physically building a miniature, materially perfect scale model of the foundational space-time of our universe.
That is exactly the philosophical weight of the paper. They're gestating a microcosmos. The rules governing the carbon sponge are the exact same mathematical rules governing the cosmos. And it even seamlessly answers massive cosmological mysteries, like the formation of black holes.
Wait, how does it do that?
They discuss a phenomenon in the sponge called lattice collapse. If you forcibly pack too much quantum information, too much entanglement, into one small, localized region of the aerogel graph, the information density fundamentally exceeds what physicists call the Bekenstein bound.
The Bekenstein bound is the absolute theoretical maximum limit of information you can physically cram into a given volume of space before physics just breaks down, right?
Right. It is a hard limit on entropy, and when their mathematical lattice hits that bound, the graph literally cannot sustain the connections. It collapses in on itself. The nodes sever, information can no longer propagate outward to the rest of the lattice.
Wow.
To an outside observer, that region of the graph becomes a dark singularity, a black hole.
So you're saying their carbon sponge could theoretically simulate the exact mathematical formation of a black hole?
Yeah.
Not by simulating gravity, but just by forcefully concentrating too much quantum data into one tiny microscopic spot of the aerogel.
The mathematics of the lattice collapse and the formation of a physical black hole are perfectly identical. It provides a stunning bridge between the microscopic weirdness of quantum mechanics and the macroscopic weight of general relativity, all unified within this one elegant framework.
This is, it's genuinely dizzying to wrap my head around. Let's try to pull back and synthesize the sheer scope of the journey we've been on with this white paper today.
Yeah, let's recap.
We started with a pile of bio-derived hemoglobin, literally freeze-dried blood proteins and vitamin C. We hit that organic matter with a wide-beam CO2 laser to puff it into a nanoporous sponge that is 99% empty air.
Right.
Then we use microscopic optical scalpels, femtosecond lasers, pulsing in millionths of a billionth of a second to sculpt perfect 3-nanometer dots of pure carbon-12 inside the empty pores.
We then trap solitary electrons inside those dots, perfectly isolating them in the deep topographical craters of momentum valleys to achieve mind-bending coherence times of up to 38 seconds.
All while guiding the carbon atoms with invisible electric fields and real-time blue light optical feedback.
Exactly.
We use the empty, vacuum-like air of the sponge's pores to perfectly insulate the carbon wires, and to act as highly advanced acoustic foam to scatter and absorb the microscopic earthquakes of phonons that would otherwise shake our quantum data to pieces.
Which completely eliminates the massive, power-hungry 15 millikelvin dilution refrigerator.
Shrinking a building-sized supercomputer down to a roll-to-roll spool of flexible tape that can just operate on a desk.
And we utilize the native three-dimensional geometry of that porous tape to run ultra-efficient QLDPC error correction algorithms governed entirely by classical graphene processors that are carved seamlessly right into the protective outer shell of the carbon matrix.
And if all of that engineering brilliance wasn't enough to secure a legacy, the exact mathematical structure of this carbon sponge just happens to perfectly map onto a unified theory of quantum gravity.
Right.
Mathematically proving that physical mass is just a measure of localized complexity, and gravity is nothing more than the physical tension of information dragging on the woven fabric of reality.
It is a profoundly humbling document to read. It serves as a stark reminder that the most revolutionary, reality-altering technologies don't always come from simply taking our current brute force methods and scaling them up.
You don't always win by building a bigger freezer.
Exactly, or adding more copper wires. Sometimes true advancement requires completely rethinking the material and physical foundation of the problem from the atomic level up.
Which leaves me with one final, deeply provocative thought for you, the listener, to chew on as we wrap up this deep dive. If physical reality, mass, and gravity are truly mathematically just emergent properties of a discrete quantum lattice processing information,
Right.
and we, as a species, are now actively learning how to manufacture our own highly dense programmable quantum lattices out of pure carbon. At what point of computational density does the machine